All right. So yeah, thanks for the introduction. As I mentioned, I'm Barak Nehoran. I'm a PhD student at Princeton University, working with Ron Raz and Mark Zendry, and I'll be starting a postdoc this fall with Henry Yuen at Columbia University. Excited to share this work with you. This talk is based on joint work with Tomiyuki Morimae and Takashi Yamakawa, as well as concurrent work with by Lowen Chan, who independently arrived at the same result. Now, don't tell Lowen I said this, but between you and me, our version is better. And by better, I mean that it's longer, much longer. And clearly, more complicated proofs are strictly better, right? Anyway, more kidding aside, feel free to read either of these works for details. They're both great. And so this talk is about quantum commitments with auxiliary inputs. And we'll talk about that more in a moment. But first, I know we're all from different backgrounds with different terminology, and I want this talk to be understandable by everyone. So I want to make sure that we're all on the same page about what we mean by unconditional security. So unconditional security is often associated with terms like information theoretic security, statistical security, and true love. Okay, maybe not that last one, since I'm pretty sure we're talking about cryptography here. Sorry, guys. In any case, unconditional security is a distinct concept from the other two, which are in fact closely related. And for this talk, it's crucial to understand the distinction. So let's get into the specifics. You can put it into sort of charts like this. Now, at this point, if you're familiar with these terms, you might have there to doze off, maybe text your friends about how dull this talk is. He's going into the definitions of these basic terms, how boring. But I urge you to stick with me for a moment, because otherwise you'll be really confused when I talk about cryptography that satisfies one notion and not the other. So information theoretic security, as opposed to computational, indicates that you're secure against any adversary, supposedly because the adversary just won't have enough information. And this is nice, of course, in many ideal scenarios, but it's not always possible to achieve. Sometimes we have to settle for computational security, where we choose some specific type of adversary that we deem to be the efficient adversary, and we show that this particular adversary can't break our security because of its limited resources. Now, the proof of security can take one of two possible forms. We could have a security reduction, or we show that security holds conditioned on something else being secure. Or in the best cases, we can prove security outright with no conditions. So the catch is that nearly all security proofs fall along the diagonal of this table. Either an unconditional security proof of information theoretic security, for example, like the one-time pad or quantum key exchange. Don't worry about the specific examples. There are several examples in this area. Or a conditional proof of computational security, like classical key exchange, where we choose a specific adversary and show a security reduction to a hard problem. So classical key exchange falls here, as does all computational cryptography. And this is why the term unconditional security is so often confused with information theoretic or statistical security, because for most cases, these come hand in hand. And in fact, it's hard to find examples of any schemes that fall outside the diagonal. Well, security proofs up here do exist, but are quite rare and usually not necessary. And on the other side, if we could outright prove the security of any computational cryptography, that would bring it down here. But unfortunately, there are barriers to doing this, and computer scientists have struggled for a long time to get around them. For example, with classical cryptography in particular, this would require showing that P doesn't equal NP. We do have things like the existence of hard functions, either hard to compute functions or hard to invert functions, whatever you want. But there's nothing cryptographically useful. So can we get unconditional security for computational cryptography. So our two works show for the first time a commitment protocol that falls in this category, specifically when all the parties receive a quantum auxiliary input. And I'll explain more about what that is in a moment. So first of all, commitment schemes allow someone to lock away a message that they can send to someone else and later reveal the message without being able to modify the committed message. And commitments with quantum auxiliary inputs were first defined by work in 2016 and allow all parties to receive quantum advice state as input. And this CKR construction showed security from a computational assumption, but we show perhaps surprisingly that no computational assumption is needed. In other words, that they exist unconditionally and with computational security. And to the best of our knowledge, this is the first example of a cryptographic protocol whose security is inherently computational, but yet is unconditionally secure against polynomial time attackers. All right, I'll start by motivating why we care about quantum commitments. Then I'll define quantum commitments, including those with quantum auxiliary inputs. Then I'll take you through our results and our unconditional construction. And finally, I'll mention a few variants and why it's not possible classically. So let's start with why commitments are so important for us to study.
Barak, is it okay to interrupt for questions, or do you prefer to have questions?
Sure.
Okay.
Sure, go
So
ahead.
I have a very dumb question. So how is the fact that the adversary is polytime being used if the security is unconditional?
Right. So let me go back to the slide.
Yeah, sorry, I might have missed something obvious.
Yeah. So essentially, the unconditional security just means that there's no assumption. There's not security reduction from an assumption. There's just outright proof that any polynomial time attacker cannot break the security.
Right,
but it's
the
not information theoretic.
It's
not information theoretic because it's not against any adversary, right? It's not against, like, if you run in unbounded time, you can still break it. But we prove that if you run in polynomial time, you cannot break it.
Right. So normally the fact that something is polytime is really captured by, like you're saying, it's captured by assuming that some problem is hard. So that's why I was wondering that the techniques must be very different now, because you're somehow inherently using the fact that they're polynomial time, and
yeah. So we're using the fact that they're polynomial
that.
time, but without any assumption about any hard problem. Essentially, the hard problem that we need, we prove outright that it's hard.
Right, and it's not even in the query model, so it's not. Yeah, maybe I'll just see. I'll just see how the fact that it's polytime is actually used in the proof.
Yeah, it's somewhat counterintuitive because of the fact that we're so used to the fact that we're so used to unconditional proofs being statistical.
Right.
That's I mean, ideally you would be able to show that one-way functions exist unconditionally, right? Like suppose somebody tomorrow proved that one-way functions exist unconditionally, right? Then they wouldn't make a computational assumption. This would be just like an unconditional proof that one-way functions exist. Of course, this is still very far away, but and even showing that commitment with auxiliary inputs classically is exists unconditionally. It would imply P equals NP, or sorry, P don't equals NP.
Right.
And the surprising thing is that in the quantum world, that's not the case. In the quantum world, you can actually show the commitments with auxiliary inputs exist just unconditionally.
Right.
I'll get to a discussion about how to interpret this and what this means later on.
Right.
I have slides later in the talk.
Great. Thanks.
Okay. All right. So let's start with talking about why commitments are so important for us to study. And the reason is that commitments can be viewed as a necessary assumption for cryptography to exist. So classically, if we look at the big picture in computational cryptography, it looks roughly like this, with implications between all the cryptographic primitives, all leading to one-way functions at the bottom, as well as everything equivalent to them, including commitments, which you see right next to it. And because of this, the existence of one-way functions and commitments was considered the minimal assumption, without which cryptography couldn't exist. And having secure one-way functions at least requires that P doesn't equal NP, as I mentioned, which there are no barriers to proving. In the last few years, however, a line of works on cryptography with quantum states has shown that this is not the full picture. And there's, in fact, a whole world of quantum cryptography below one-way functions, which may exist even if P equals NP, all leading to quantum commitments at the bottom and everything equivalent to them. And so back in the 80s, when it was discovered that quantum key agreement could be made unconditionally and statistically secure, there was hope that we could do the same with other quantum primitives like commitments. Now, ultimately, we now know that commitments can't be statistically secure. They must be computational. But there's no reason why the security can't be unconditional. And this is one of my main messages for you. There's nothing preventing us from doing this, since it won't imply that P doesn't equal NP, and so the known classical barriers aren't really an issue. But despite the fact that it cannot be statistically secure, there's nothing preventing us from showing them unconditionally. And so quantum commitments with their position at the very bottom are prime target for this, of course, because this so-called low-hanging fruit, so to speak. And our proof that this is possible when all parties receive quantum auxiliary inputs, notably despite the classical barriers, may give us hope that we can do this in the plane setting as well. Okay, now let's define quantum commitments as well as the variant with auxiliary inputs. So in the quantum case, commitments in their most basic form look something like this. You have two quantum states representing commitments either 0 or 1. But let's focus on one of these two quantum states. So, at any point in time, you have just either one of these. So let's just focus on the red one on the left. So this state has two registers, D and C. These are both states on the same two registers, D and C. And these registers are entangled with one another. The C register will eventually will use it as the locked box that contains the message, and the D register will use it as the key to opening. And for those who are wondering, I'm depicting them in what's called the Schmidt basis, because I find this to be the most intuitive and visual way to depict entanglement, where all these lines here mean that if there's a line from, for example, from 1 to 4, that just means that you have part of your superposition includes the the state 1, 4, and another part of your superposition contains a state 2, 8, for example. So you have a superposition over all these different pairs. For those who aren't familiar with the Schmidt basis, don't worry too much about this, but just know that we have a superposition over all these different connecting segments. And also note that I'm only going to talk about non-interactive commitments, where Alice just sends a message to Bob to commit and a message to Bob to decommit. I'll talk about this in a moment, but if that bothers you, then feel free to rest comfortably knowing that this is without loss of generality, because every commitment can be framed this way. All right, so say Alice wants to commit to the bit 0. So she chooses the first state, for example, and sends the C register to Bob. So this is called the commit phase. And later on, when she wants to reveal her commitment, she sends the D register to Bob, at which point he can see that what was committed to, and he can verify that it's valid. And the security is all about what happens between the phases. So hiding says that in Bob's view, he cannot tell whether Alice committed to a 0 or a 1. And binding says that Alice cannot act on just her register, on just her view, to change her mind about which one she committed to. So she cannot manipulate the state from 0 to 1 just by acting on her side. And commitment with auxiliary inputs is just the same, but where both parties have access to copies of some fixed quantum state. And these may not be efficient to prepare. So imagine that there's all these states and available that an unbounded number, and they can just Alice can download as many copies as she needs, which she can then use to prepare the entangled state that she can use to commit to Bob. And at any point, they can download additional copies, but they don't need to until the reveal phase, when Bob can download more copies to verify the commitment. Right? Any questions about the definition?
I have a question. So maybe you mentioned it, or you're going to mention more about it later, but how exactly are these states being used in the protocol?
I'll get to more details about how we construct it, but in general, the definition just says that you can use these states in all phases of the protocol. So, for example, you can use these states to create the quantum states that you'll use for the commitment, and you can also Bob can also use it to check, to do the verification process at the end, and you can use it in any part of it. Whenever you have these quantum auxiliary inputs, the model is just saying that you can use these states whenever, at any state, at any phase of the protocol. Does that answer your question?
Yeah, thanks.
Okay, so I mentioned that we provide a construction of this kind of commitment whose security is unconditional and computational. But why not have statistical security? Well, that's because even in this setting, commitments cannot be statistically secure. To see why, suppose that the two possible states in Bob's view are statistically close. So I'm just depicting psi 0 and psi 1 at the top. They never have this both states at the same time, right? So like they either have psi 0 or psi 1, right? So they just choose one of them, but I'm depicting them side by side so we can compare them. And suppose that these, on Bob's view, these are both statistically close. So the Bob can't tell them apart. And this means that this commitment is statistically hiding. Then there exists an operation, a local unitary, which converts the 0 commitment to a 1 commitment, allowing Alice to cheat and break the binding security. And this is by Ullmann's theorem. And so this breaks the security of the commitments, which means that such a commitment that's both statistically binding and statistically hiding cannot exist, even when you have these auxiliary inputs. The same principle applies. So if we want to secure commitment, we need at least one of either hiding or binding to have only computational security. This doesn't prevent us from showing the security unconditionally. And in fact, for commitments with quantum auxiliary inputs, this is what we managed to do. Now let's take a quick overview of the results and our construction. So we show that these commitments exist unconditionally, and with computational hiding and statistical binding. So recall that I mentioned that they were originally constructed from a computational assumption, namely that QIP is not contained in QMA. But surprisingly, we show that this assumption is not necessary, or really any assumption for that matter. We just prove it outright. So here's a construction. So we start with a length doubling function h, and construct the state that has a superposition with all the inputs x in one register and all the outputs h of x in the other. And this is the commitment to 0. And the commitment to 1 is just the fully entangled state on the largest support. And note that the second state can be efficiently prepared by Alice. Well, the first state may be inefficient. It depends on the function h. So we just provide it as auxiliary inputs to both parties. All right, so during the reveal, Bob can't uncompute the first state size 0, like he would do with a standard commitment. In most commitments, he would just run the circuit that Alice ran, but in reverse, in order to verify. But he can't do this here because he doesn't have this the circuit. The circuit takes in an auxiliary input, and this is not a reversible operation. But he can instead run a swap test with the other copy that he received as input, and we show that that this still allows it to be statistically binding and computationally hiding. So
just to sorry, but just to quickly check, so the description of capital H is somehow related to the input auxiliary states. Is that correct?
Yes. So these auxiliary states are just literally this red state here. So just like the auxiliary inputs that they get is just as many copies as they want of this red state.
I see.
Which means that Alice doesn't need to do anything to prepare it, right? Alice just like takes this state and just uses it, right?
I see. And
If
the other one is easy to prepare for Alice. Okay, got it. Good.
Right.
Good.
This one's really easy to prepare.
Okay.
It's just uniform superposition.
Just entangled. Yeah. Okay. Good.
Right. So Alice either prepares this blue state, or if she wants to prepare the red state, she just uses the state that she already got as input. Right.
Okay.
And this is why, say up here, when Bob wants to do the verification, he can't actually uncompute because there isn't necessarily
you just
an
want to do a
efficient
swap.
circuit.
Got it. Yeah, good. Okay.
This takes some work to show. It takes some work to show that the swap test still works for security, but we're able to show that this is still secure in this way. Okay, so what were you asking?
So I think you'll explain the why it's binding and hiding as well, I guess.
Oh,
in the comments
sure.
slides, yeah.
Right. So binding is pretty straightforward because Bob's views are statistically far, right? Essentially, in this case, because it's length doubling, there only a small negligible fraction on his side, right, will appear. Only a negligible subset, for example, 1, 3, 5, 8, and 10, right? But in general, because if it will be a length doubling function, like in general, only it will only have support over a negligible fraction of possibilities. Whereas here it has full support. So they're statistically far, which means that it's it's pretty straightforward to show that this means that it's computationally that it's statistically binding.
Okay.
And so we just have to show hiding. So in Bob's view, he sees one of two distributions. One is sparse, and the other is uniform. And we just want them to be indistinguishable. So we use a sparse pseudorandom distribution that is secure even with quantum advice. And this is, this is pretty much the definition of the sparse pseudorandom distribution. But I'll get more into detail in just a moment. But does such a thing exist unconditionally? Well, so yeah, we show that these sparse pseudorandom distributions can exist unconditionally with quantum advice. So what are these classical, what are these sparse pseudorandom distributions? So the classical version of this was defined in the 80s by Goldreich and Kravchuk. And these are distributions of negligible support, but nevertheless are indistinguishable from unitary. And here the adversary is still classical. So they showed that these sparse pseudorandom distributions exist unconditionally. Well, great, that's what we wanted, right? But not so fast, because it turns out that these are not cryptographically useful. And in particular, can't be used to build commitments or really any other cryptography. And the issue here is that there's no generic way to classically verify that a sample comes from a distribution. For example, say I give you the number, I don't know, 37. Can you tell me which distribution it came from? Probably not. So we generalize this to the post-quantum setting, where both the distinguisher and the advice are quantum. And we show that post-quantum sparse pseudorandom distributions exist unconditionally. And in fact, nearly all length doubling functions work here. If you just choose one arbitrarily, either arbitrarily or at random, or choose the best one, whichever one. And you do this using two different techniques. So the first is using recent work from Liu on the quantum random oracle model with quantum advice. And the second is using what's called the matrix Chernoff bound for the operator norm.
But wait, I'm a bit confused, because on the one hand you're asserting it's unconditional, and on the other you're saying it's in the random oracle model. So I'm missing the connection somewhere.
Yeah, so that's a great question. So even though we use results from the random oracle model, we use proofs that are shown in the random oracle model. Here we don't have a random oracle, so this is not in the random oracle model. But we use some techniques that were developed in the random oracle model.
I see. It's because you don't have access to the functions directly. I guess you're just getting samples, so
Yeah.
somehow you can.
Right. So yeah. So essentially, you can think of this in this way, like, right, this length doubling function h can be viewed as a random oracle that is inaccessible, right? You never get access to h.
Right.
You only see these quantum states that maybe tell you some information about h, but they don't reveal the full information. So they're not exactly like, they're not the same model, but it turns out that some of the techniques that are developed in the random oracle model are useful for us.
Wow. Okay. And the fact that it's polynomial is appearing where in the number of samples. So the PPT, the classical distinguisher gets exactly one sample, or can it ask for multiple samples?
So in both cases, like, you have any polynomial, if you want a polynomial adversary, then they can access polynomially many samples, right?
I see. So if it was exponential, so basically it's coming from sample complexity, right? Somehow the fact that it's unconditional, is that the way to think about it, do you think? Or?
Right. So so one way to think about it, is in terms of like how many samples of the auxiliary input you need.
I see. Okay.
Mm-hmm. But of course, if you're polynomial time, you can only access a polynomial number of samples.
Exactly. Yeah. No, but just that the fact that it's polynomial time is often very hard to, like, you have to use either queries or samples or something. So that I was very curious how that's modeled in, but somehow it's appearing in a very beautiful, natural way, right? Like, you don't have to add it as a model, but it's somehow just from the interaction, it seems.
Yeah, exactly.
In the model. Okay, very nice. Okay, thank you.
And I'll talk in a moment about this, but like, classically, in the classical version, not only like is this classical sparse pseudorandom distribution not useful, but really you cannot get classical auxiliary input commitments unconditionally, at least not without showing the p doesn't equal to np. So the fact that we can do this in the quantum world is, I would say, is quite surprising.
Right.
I certainly thought when we initially figured out this proof, I initially thought that it must be wrong.
Yeah,
we must have a bug somewhere. We went over and checked it multiple times to figure out like all the logic, and we were like, this has to be wrong. There's no way.
Right.
So
very cool. And so commitments are also universal in this model, in this shared like, can you build all of MPC from this? Is that?
Yeah, so we'll get to that. Yeah, we can give build a other primitives in this model, and I'll get to that in a moment.
Sorry. Yeah, please carry on. I'll shut up
Okay.
now. Yeah.
No worries. Yeah, so so as I mentioned, like we there's two possible proofs that either through using these random oracle techniques, which, as I mentioned, they're not we don't use the random oracle model, but some of the techniques are useful. But you can also prove it more directly using matrix turnoff bounds. And as we just shown, unlike in the classical case, these post-quantum sparse pseudorandom distributions, they do in fact yield unconditional commitments. And that's just because, unlike in the classical world, you can use a swap test to verify distribution. Like in the classical world, if I give you two samples from the distribution, there's no way to check that it came from the same distribution, whereas in the quantum case, we have a swap test. And this is kind of like the main difference here, why quantum allows us to do this. And so finally, I'll end with a bonus variant, as well as why it's actually impossible to build these commitments classically.
But before you go on, just to quickly ask the silly curiosity, which is that you cannot then probably have swap tests for mixed states that are as good as those for pure states, right? Because
yeah, that's a good question. So so our auxiliary input model, it allows, I guess. There's no not necessarily a reason why it wouldn't allow for mixed states, but we construct it using pure states, right? Our construction uses pure states.
right, because of course, if it was like entirely mixed, like fully mixed, then like it was just classical, right? Then of course your argument says that it could not possibly work because of the impossibility. So okay, good.
Yeah, so it's kind of like, it's inherently using the fact that there's pure states in order to be able to do the swap test. Yeah.
Right, thanks.
So yeah, I mean, this actually leads to the very next slide. So what if I mentioned that we treat this auxiliary input as a pure fixed quantum state for every value of lambda, and so what if we let the states be sampled at random? So let's say there's some trusted setup algorithm, Tom, that samples the states according to some distribution. And he still gives the same identical states to both parties, right? So now it's not exactly what what you mentioned is they're not mixed states; they're just pure states that are sampled ahead of time, right? So like say at the beginning of time, Tom just decides on some fixed pure state, and then just always gives the same pure state to both Alice and Bob. And we show that in this setting, we can actually get statistically secure commitments. So commitments that are both statistically hiding and statistically binding. And well, this is also probably surprising, but the reason why this model we can get around the impossibilities is because here Alice does not have Bob's verification, which means that that Ullmann's theorem does not apply here, and the standard impossibility kind of breaks down. Any questions about this other model? I would say this one is not as surprising as the unconditional computational one, but
So why is it not surprising? Because
it's not as surprising because essentially or the standard impossibility for statistical commitments uses Ullmann's theorem, and this really depends on Alice having a purification of the complete purification of Bob's register. So if she has a
So if you remove
purification
that,
of
you're saying that it's, I see, okay, got it.
yeah, so now the impossibility just like doesn't, like the statistical impossibility doesn't exist. So if you can do it statistically, then of course it's, usually you can, if you can do statistically, you can also do unconditionally. So this is not as surprising. I'd say the more surprising result is our main one that I mentioned before, where in the auxiliary input model, like the decided auxiliary input model, we can get computational security, but unconditionally. And there it doesn't get around the Ullmann's impossibility theorem. It doesn't get around it. Essentially, like, the impossibility theorem only says that it can't be statistical. It never says that it can't be computational.
Right. Yeah, it can't be unconditional. Yeah. So I think I sort of messed up the models in my head. So the previous one was that you get so everyone gets the same state.
Yeah.
And the state is fixed.
Yeah. So we have a fixed state. Yeah, so we have a fixed state. So for example, just choose the best length doubling function, right? So there's some length doubling function that actually, most length doubling functions will work, in fact. So choose one of them, arbitrarily fix it, right? And now
there's no
always
distribution
whenever you run, there's no distribution. There's just fixed states psi that both Alice and Bob gets, right? And then this is always like every time they run the protocol, there's always this fixed states, right? There's never like, it could never have been anything else.
And can this state have an efficient description?
So it cannot have an efficient description, because if it could have an efficient, at least not one that allows you to recreate it, because if so, you could kind of get rid of the auxiliary inputs by just recreating.
Exactly. Yeah. So somehow I see. So somehow, okay, got it. Thank you.
And so in this model that I'm talking about here, it's essentially slightly different, where essentially instead of a fixed quantum state that everyone receives, you just sample the states at random ahead of time. So ahead of time, like, you sample, you sample the state, and it's just you just say that, like, with overwhelming probability over the choice of states, this will be secure.
Right. And of course, if you allow the malicious party to hold the purification, then again, Ullmann's theorem will apply. Okay, good, got it.
Yeah. Mm-hmm.
Thank you. Yeah.
All right, so finally, you might wonder why we couldn't dequantize this and use classical randomness instead of quantum. So there are two main settings that you might consider. The first, with an inefficient pre-processing step that introduces that produces the random auxiliary inputs, and the second with either correlated or uncorrelated random auxiliary inputs. And in the first setting, Chan's concurrent work shows that this would imply that P doesn't equal NP. So the barriers shoot down any hope of unconditional security here. And in the second setting, we show in our work that statistical security is impossible whenever the correlations are either too low or too high, meaning that the correlations must have some structure. And this structure can be exploited to break security if the players can see each other's inputs. And in our case, all the auxiliary inputs are public and it can be viewed by anyone. So for example, if the auxiliary inputs that was given to Alice is leaked to Bob, this doesn't break security. Everyone sees the auxiliary inputs. Any questions about these possibilities? Okay. Okay, so to recap, we show, oh wow, these lovers really are committed, huh? So to recap, we show that if all the parties are given quantum auxiliary inputs, they can implement commitments with computational security, but crucially without any unproven assumption. And this is despite the previous belief that they required assumptions. And to the best of our knowledge, this is the first example of computational commitments that are unconditionally secure, as well as the first example of such a protocol when all the parties are polynomial time. And as a takeaway, I hope this brings us to reevaluate the need for computational assumptions in quantum cryptography. Do we really need them, or can we do away with them altogether? Specifically, does this mean that we can build commitments in the plane model unconditionally? Well, possibly. It won't be a direct implication of the auxiliary input setting, but as far as we know, since classical barriers don't apply here, there's no reason why we shouldn't be able to build computational quantum cryptography unconditionally. And with that, I'll thank you for your time.
Thank you so much for the lovely talk. I mean, normally we would applaud, but we're in different rooms, so I think it's a bit hard to do that. But I think I speak for everyone when I say, oh yeah, there are like emojis for clapping, but okay, whatever. Yeah, thank you so much for the lovely talk. If people have any questions, maybe now is a good time to ask them if you haven't already. I asked a lot of questions, so I think I'll let others.
I guess I'm curious, like, what have you thought about other kinds of protocols, like, say, I don't know, oblivious transfer, or I mean, you showed that diagram before at the beginning, and just you have here in the Outlook, you say, oh, we can build other quantum crypto protocols. Like, what have you thought about?
Oh, that's a great question, and so yeah, we can. So we show in the paper how to do, I believe, a certain version of oblivious transfer that also has these auxiliary inputs, and as well as how to do I believe these a certain version of let's see, what else do we have in the paper? It's yeah, so we show how to do a few other primitives in the paper that are in this this kind of lowest level of the cryptographic hierarchy. It's an open problem whether other cryptographic primitives can be done in this setting. There's follow-up work that has shown how to build one PRS, which are pseudorandom states that are secure against if you have a single copy. And let's see what else. Yeah, there's also these like I think bounded copy, some form of bounded copy multi-copy PRS. But yeah, this is in follow-up work where you take this auxiliary input and you make it a hard random state. And so for if it's a hard random state, you can use it to build these one PRSs and PRSs with bounded copies. And I think there's also impossibilities for some primitives. I think for like the full multi-copy PRS, I think there's impossibility in the hard random auxiliary input model, but I'm not sure if it's also applying in the general setting, but yeah, we also show that you can build, I think, some kind of zero knowledge for NP with auxiliary inputs. So yeah.
Thank you. Like, it seems like this auxiliary input assumption, it's very, like, I mean, I don't think it's necessary, but it's used a lot, I guess, in these proofs, right?
Yeah, so it's really necessary to have the auxiliary inputs in order to be able to prove unconditional security. Because I mean,
Okay.
it's at least for the proofs that we know, it's really inherent that we have to have these auxiliary inputs. If we didn't, then we'd be able to show kind of in the plane model of this unconditional cryptography. Which as I mentioned, there's no barriers against it. So maybe tomorrow somebody will come up with a security proof in the plane model of for commitments. I personally, I think that's unlikely. Personally, I think that the correct what actually is true is that there probably are barriers that we haven't explored. We have these classical barriers, like, the barriers against P doesn't equal NP, for example, the naturalization barrier or the relativization barrier. We have all these barriers against showing P equals NP, to say that, like, if you want to show that P doesn't equal NP, you would have to, you can't use proof techniques like this, you can't use proof techniques like that, it can't work like this, so there's like all these barriers, but none of them apply here in this heading, right? Like, because quantum cryptography, these kinds of quantum cryptography can exist even if P equals NP. They can exist, in fact, whether P equals NP or P doesn't equal NP, which means that these barriers, classical barriers, just don't apply here. So what I believe is the right thing is that we probably should investigate barriers in quantum cryptography. Like, can we find barriers to showing unconditional security in quantum cryptography? And probably there are these quantum barriers that just haven't been explored, which would mean that probably showing that unconditional standard commitments exist is probably a ways off. That's my guess. But because, as far as as of the current moment, there are no barriers. If somebody tomorrow published a paper that says, here's a proof, here's an unconditional proof that quantum commitments exist, you wouldn't be able to point to any, well, you had to have gotten around this, or you haven't have gotten around this. You'd be probably just say, well, hey, maybe they're right. But yeah, so that's I think it's a really fascinating direction to investigate, like whether we really need computational assumptions for this minimal quantum cryptography, or whether we really need more barriers.
Right. Sounds very exciting. Thank you.